Hello everyone, the topic of my presentation is bridging adsorption behavior of confined methane across scales. I am Lingfu, a PhD candidate, and I work with my advisor, Dr. Simon Ariana at the University of Wyoming. The research goals of this work are to investigate adsorption behavior of methane in nano-sized pores by using a scale translating simulation framework. In this framework, based on phase behavior of methane, we conduct our molecular simulations and then use the molecular simulation results as benchmark data and coupled with phase behavior to translate adsorption physics across scales by using lattice Boltzmann method, that is from microscale to meso-scale. And grand canonical Monte Carlo simulation method is a widely used molecular simulation method to study adsorption. In this method, a GCMC domain is virtually connected to a box system with specified fluid properties. By means of inserting or deletion or rotation or translation of molecules in the Monte Carlo simulation region, confined fluid will obtain the same chemical potential as a specified box system. But first, we need to validate our GCMC simulations. In this validation part, we consider our GCMC domain as a pure fluid systems with full periodic boundary conditions. So the fluid here are expected to obey bulk phase behavior. For comparison, the input data of fluid gas coefficient are calculated by using two equations of state, SBWR equation of state and PR equation of state. At given temperature, pressure, and fluid gas coefficient, the obtained bulk fluid density are compared with reference data from NIST and as shown in the upper right figure, and output pressure is also compared with input pressure as shown in the lower right figure. It is observed that the fugacity coefficient calculated based on SBWR-US produced better predictions than PR-US. Moreover, we could further slightly tune the values of input fugacity coefficient to find the optimized values, which can produce best prediction. Then, confinement is considered by using two carbon sheets with 5 nanometer apart to represent organic nanosolids. And the density distributions from GCMC results are shown on this slide. Here we can observe the adsorption layers with high fluid density near wall surfaces, while fluid density around pore center is still at bulk values. Then we change pressures from 2 megapascal to 30 megapascal, and pore size at 5, 7, and 10 nanometer pores. It is observed that as pressure goes higher, adsorption peak becomes higher, which makes the second and even the third adsorption layers start to form. However, the adsorption layers are independent with pore size, which means as pore becomes wider, adsorption peak and the number of adsorption layers don't change. Then we extend our study from slit nanopores to irregular nanopores to study the impact of pore geometries on adsorption. Here we consider two types of irregular nanopores, the nanopores with triangle structure on surface and the nanopores with rectangle structure on surface. From simulation results, it's observed that geometries do impact density distributions. For example, in these blue dash circles, we can observe higher fluid density, higher density peak in the density profile because the force field of the two neighboring walls overlaps at this kind of corner, which consequently causes a lower potential energy to let fluid molecules stay there and therefore show higher density. By contrast, In the blue or in the red dashed circles here, density becomes smaller because the higher potential energy contribute to fluid molecules escaping from ore. So far, we already know that molecular simulations are able to reveal fundamental physics, but its application is limited in relatively small and simple systems due to computational expense of tracking evolution of area particles. However, lattice Boltzmann method as a meso-scale simulation method is a good candidate to handle such problem. In LBM, the governing equation studies distribution function of a group particles G at discretized lattices with limited moving direction, which rather than the motion of every single particle in a whole space as molecular simulations. So in this way, LBM show much improved computational efficiency. And intermolecular forces, such as fluid-fluid and fluid-solid intermolecular forces, are characterized by LB free energy model, where intermolecular forces depend on chemical potential gradient and density gradient. Also, under isotherm simulation conditions, chemical potential gradient may be calculated based on fluid viscosity gradient, and in this work, viscosity is determined based on SBWRUS. In calculating the local gradient of the fluid property in this forescheme, we consider the most neighboring and the second neighboring layers of lattices to reach higher order of simulation accuracy. For the treatment of fluid-wall interactions, when a neighboring lattice at I-1 is a solid lattice, we calculate mu I-1 equal to GFS times mu I, where GFS is a tunable fluid-solid interaction parameter. When its value is smaller than 1, it will create a region with lower potential energy to produce attractive forces, which is to mimic what we observed from molecular simulations. And we applied this LB model to slit pores, and LB simulation results are in good agreement with GCMC reference data at various pressure and pore size conditions, as shown on the left-hand side of this figure. It is also found that the values of GFS varies with pressure, but it is independent of pore size, because higher pressure produce larger attractive forces, which consequentially require a smaller value of GFS to produce such larger attractive force. But attractive force is independent of pore size, you know. Armed with the values of GFS as a function of pressure, we extend the simulation domain to those irregular nanopores. As presented on this slide, the LB model is able to capture the impact of geometries, as we observed from molecular simulations, for example, the higher adsorption peak at corners and the lower adsorption density value at these edges. Next, we quantitatively compare LB and GCMC results. We sum up the quantity of methane contained in the nanopores and compare LB results with GCMC reference data, where we set 100% as GCMC reference data in each scenarios, and the two bar graphs show that LB simulation produced good agreement with GCMC reference data, and the orange bars are the LB simulation results. Meanwhile, if we do not consider the adsorption as shown as the blue bars, we will significantly underestimate the quantity of the reserved methane in these irregular nanopores, may be up to 50% error. So to this end, we may conclude that we accomplished bridging adsorption behavior of confined methane across scales from molecular simulations to LB simulations. Last but not least, this work is supported as part of CMCUF funded by US DOE. Thank you for your listening.